Hey everybody, Dr. A here, and in this video we're going to be exploring another example of internal torque moments. So let's go ahead and get started. In the given information, we're being asked to draw the internal torque diagram for the shaft. So here we have a shaft with a fixed connection at A, and it's 5 feet long, and over its entire length we have a uniformly distributed torque moment of 30 pound-feet per feet. So this is a torque moment that has been spread out over the length of the shaft. And so how do we accomplish this task of drawing the internal torque diagram? Well, an internal torque diagram is a lot like an axial load diagram, or we sometimes call that an internal normal force diagram. It's also quite similar to a shear force and bending moment diagram. This gives us the graphical representation of the internal torque over the length of the member, okay? So let's go ahead and write that down. Under solution, an internal torque diagram shows the variation of torque with length, okay? Now, the first thing we're going to need to get this going is the torque reaction at the fixed connection A. So can we figure that out just by looking at it? Well, yeah, hopefully so. All you have is the uniformly distributed torque over a 5-foot length. So hopefully we can just look at this and say the torque reaction at A, we can call that TRA, is equal to what? Well, that's just going to be equal to 150 pound-feet. We know that because if you take 30 pound-feet per foot and you multiply it by 5 feet, you get an equivalent single torque moment that's really located at the center of the shaft, but it's a equivalent single torque moment of 150 pound-feet. And so by equilibrium, we know that the torque reaction should be equal to 150 pound-feet, but going in the opposite direction. Okay, so hopefully that basic statics is obvious to you. So the next thing we're going to do is go ahead and draw our set of axes. So here we can say X in feet, and we can say this is torque moment in pound-feet, okay? And then we need to establish some directionality here, okay? So here I'm going to say going counterclockwise is positive, and I'm going to base this on a viewpoint that I'm going to establish right about here. So let's say that we stick a little viewpoint, a little eyeball here, and we're looking towards the end of the shaft. And so things going counterclockwise from this viewpoint are what we're going to call positive, all right? So the first thing we encounter, if we move from left to right, you know, we've got point A here. That's the fixed connection. And then, you know, we got the 5-foot length out here. So the first thing we encounter is TRA, all right? And from this viewpoint, TRA is going counterclockwise. So that means we're going to pop up to a point equal to 150, okay? Now, the next thing we encounter is the uniformly distributed torque moment, and it, again, has a magnitude of 30 pound-feet per foot. So that means every linear foot of shaft is going to be experiencing 30 pound-feet. And notice that it's counteracting. This 30 pound-feet per foot is counteracting what the reaction is. Or you can think of it the other way around. The reaction is counteracting the applied torque, all right? But in either case, what that means is this diagram is going to give you a linear decreasing slope, all right? So you're going to have a linear decreasing slope that ends at 0, all right? Now, does that make sense? Well, yeah. I mean, every linear foot of shaft, you're going to have a relief of 30 pound-feet. And once you get all the way out to 5 feet, that relief will give you a net 0. So one way you can think about this is the change of torque is going to be equal to what? It's going to be equal to 30 pound-feet per foot times 5 feet, which is 150 pound-feet. So that means that the torque when x equals 5 feet is going to be equal to that initial positive 150 pound-feet, and then we're going to say minus delta t. And again, the minus is because the 30 pound-feet per foot is going in the opposite direction or clockwise compared to TRA, okay? Another way of doing this is describing delta t as a negative in front and then saying plus delta t with the negative built into the 150 up here. In either case, you get the torque at x equals 5 feet to be 0, and that's represented by the closure at 0 here. And then of course, like our axial load diagrams and like our shear and moment diagrams, we typically shade this in. Okay, so that's our final answer. If you found this video, please hit like and subscribe and be on the lookout for other content similar to this. Thanks for watching.